Hello everyone. A very good morning to all of you. So can you see the slides? Can one of you please confirm?
Yes, sir, it's visible.
Okay, good. So before we start, let me just make an announcement that we'll be having the final class test for you, which will contain this part of the this data link layer that we are talking and the design of the routers that we left for the last class test. So on this topic, we will be having your final class test that will be on this Saturday. Mm, the date is on 11th, not 11th, 11th is a Sunday, on 10th. Okay, so on 10th, uh, there will be this final class test, and I think I should be able to wrap up the course by next class itself. So that way, by this week, we will complete all the content of the class and all the class test. Okay, so for the next week, I will just check this last two answer scripts. That means for the class test 4 that I am currently evaluating, and for class test 5 that will share by the next week, by early next week. And then if you have any query, anything, we can answer that and accordingly wrap up the course. Okay. So that is the kind of plan for the remaining things. So please be prepared for the class test on this Saturday on 10th on the topic of this router design and the MAC layer. So sorry that I have to take two class tests in short gap compared to the earlier class test, but I just thought of to finish everything by this week rather than pushing it to next week. So I hope that will be fine with all of you, and that is the kind of broad plan. Regarding the grading plan, we have not decided yet. I will discuss that with RSC and let you know. Maybe I'll let you know by tomorrow. So these are the kind of broad plan. With that, we'll go and wrap up the course. Okay. So anyway, so let us then continue with a part of our discussion that we are having on the error detection code and the error correction code. So even today, I may not go till 12 because I have planned to cover a part of it, and the remaining part we can cover in the next class. So typically, what I have seen that in the normal lectures, in the board work based lectures, it takes much more time compared to whenever we are doing this kind of online lecture, because in online lecture, one of the main problem that I face is that I cannot see. Well, so typically in a in-person class, I could have seen the students, could find out the blank faces where they are not being able to follow and repeat some part. But here that was not possible. So that's why that is my request to all of you, that if you have any doubt, feel free to stop me anytime and ask me the question. Okay, so even later on, if you have any doubt, feel free to drop me an email or ask it over Microsoft Teams. Okay, so in the last week, we have seen the error detection code, which basically add a few additional bit with your data word to generate the code word. And then that code word is transmitted over the network, and the code that we are sending with the code word that help us to detect whether certain error has happened during transmission or not. So the type of code word that we have seen for error detection is the parity check, or rather single bit parity check, where we compute the parity bit based on whether we want a odd parity transmission or whether we want an even parity transmission. And then then we talked about multi-dimensional parity check. Okay, so in case of multi-dimensional parity check, we have we have seen that we can send a set of parity bits to detect the errors, and then we have checked the computation of checksum. In case of computation of checksum, again we send a set of bits, additional bits to compute the checksum, and finally we have seen the checksum based on cyclic redundancy check or CRC. Now, the important point that I have mentioned in the last class, trying to iterate it again, that as you are moving from a simple method to a much more complex method, where you have to send a number of additional bits. So in case of single dimensional parity check, you have seen that you just need to send a 1-bit data. When you multi-dimensional parity check, you have seen that you need to send more number of bits. With checksum and cyclic redundancy check, again the number of bits that are appended to the data word becomes more, and that way your effective utilization of the bandwidth gets less because you are sending more amount of redundant information with your actual data that you want to send. Okay, so these additional bits are also consuming some amount of bandwidth. So that way, although your efficiency is getting reduced a bit, but on the other hand, we are able to transfer data in a much more sophisticated way, in a much more reliable. Okay, so that is the kind of advantage which I have by going with complex method for error detection. Now, whenever we are moving towards error correction, we'll see that we can go with we need to send further additional bits for correcting the error. But again, that will give me the advantage that in a highly noisy channel, I could have saved the data from retransmitting. Means where there is a possibility that every individual single frame that you are transmitting, that will go through an error. Then by using error correcting code, you can save it. Okay, you do not need to retransfer every individual frame, which is particularly the case for wireless channels. So whenever you are working on with Wi-Fi, the Wi-Fi channel is so noisy that almost every frame observes some kind of bit error. And that way, if you just rely on that kind of retransmission based on the acknowledgement, then the problem is that you have to transfer or you have to retransmit a large number of frames. So rather than that, what we prefer that well, we can put certain additional bits on the frames such that will help me to do the forward error correction, and that will help me to recover from the error at the receiver side itself rather than retransmitting the frame again. Okay, so that is the kind of advantage you get. Well, so let me then discuss about the different kind of error correcting code. So the typical type of error correcting code that we have. So assume that a frame consists of M data bits and R check bits. So these R check bits are the additional bits that we are appending with the data bits for error correction. Now there are two types of codes that we have. One we call as the block code, and the second one we call as the linear code. Now in case of block code, so these R check bits are computed as a function of the M data bits. So I take the M data bits together and then apply certain function to compute the R check bits. Another different type of code is that the linear code. So in case of linear code, what we do that these R check bits are computed as a linear function of the M data bits. Right? So for example, the XOR with the modulo 2 arithmetic. Well, so typically these block codes are much more complex than a linear function. And in case of the linear code, you apply a linear function, and by applying the linear function, we compute the code. Now, in terms of these error correcting codes, these R check bits, as I have mentioned, these R check bits are sent with the data bits for correcting a single or multiple bit errors during the transmission. Now, the most important kind of error correcting code is based on a concept called Hamming distance. So what is this Hamming distance? So Hamming distance is basically in definition, it is the number of bit positions in which two code word differs. That was defined by Hamming in 1950s. One example is that assume that you have these two code word 11001101 and 01001010. So typically Hamming distance means the bit positions where these two bits differ. Now if you do an XOR, you can find it out. Why? Because if both the bits are same, say if both the bits are 1 in both the code words, say for example this second bit, it is 1 in both the cases of code word, then in XOR you will get a 0. Similarly, if both are 0, you will get a 0. But if they differ that one is 1 and another one is 0, then you will get a 1. Now, if you do a XOR and count the number of ones in that XOR, you can find out the Hamming distance. Say in this case, the Hamming distance is 4. That means in the 4 positions, that means this first, their second, third, fourth are same, fourth, fifth are same, 6, 7, 8. In these positions, they differ. Yes, so that way my Hamming distance is 4. Now, the core idea of using Hamming distance for code word generation is that if two code words are a Hamming distance d apart, then it will require d single bit to errors to convert one into another. So that means, say for example, I am transmitting this first code word 1, then what is the possibility that due to a bit error, it will get changed to code word 2? Well, now if I ask this question, then you will see that to change code word 1 to code word 2, what you need is that you need to change 4 different bit positions. Okay, you need to change the first bit position, then the 6, 7, and 8 bit position. That means you need to flip those bits to receive code word 2. So that way, if two code words are having distance d apart, then you need d bit flips to convert one code word to another. Now, what is the idea for Hamming distance? Say Hamming distance can also be used for error detection as well as error correction. Now, in error detection, the idea is something like this. That means I need to have two code words in a distance d such that I can detect the errors. Fine. So, say for example, if you have m bits data, the number of possible m bit data messages to the power m. Well, so that means with m bit of data, you can get 2 to the power m different possibilities of messages. Now, with m plus r code word, so we are having m data word, m bit data word, and m plus r bit code word. Now, with m plus r bit code word, the number of possible code words are 2 to the power m plus r. Well, now the thing is that among this 2 to the power m plus r, all the code words are not valid code words. Okay, so we can have 2 to the power m different code words corresponds to 2 to the power m different messages. Well, so that means I will be getting more number of code words compared to the number of data words that I can have with m bits. Now the remaining code words are invalid. So what we want to detect or what we want to do in case of error detection, we want to map multiple code words to a single data word in such a way so that they represent the same code word and not different code word. Well, now to detect d-bit errors, what you need to ensure? You need to ensure that the Hamming distance between two valid code words is d plus 1. Now remember that if the Hamming distance between two valid code words is d plus 1 and we are having d-bit error, what does it mean? It means that if you have a maximum of d-bit error, then you can get the code words which are in this radius. Okay, so that we can represent graphically. Now that means all these independent code words which are being generated, well, that should map to the same data word. Otherwise, you will have a confusion. So if you have a code word, say if you have a code word here, okay, then in that code word, you will have a confusion that whether this code word belongs to this blue code word or not. Why? Because with a d-bit error, you can reach from this code word to that code word. Well, so that way, with a d-bit error, the things that you are receiving at the receiver side, you will not be able to understand that whether the same thing has been sent by the sender or not. Okay, so assume that this is code word C1 and this is code word C2. Now, if they are less than d bit apart, and if you have some transmitted C2, it might happen that because of d bit error, you receive C1 and you do not know whether C1 is valid or not. So that way, I need to have a code word which is more than d distance apart, so that even after having an error, the code word that we are getting, it is non-overlapping with the code word with a second code word, with a second valid code word. Okay, so that way we'll be able to uniquely identify individual data words from the code words. Clear? Any doubt about this? That why do we need Hamming distance d+1 between two valid code words to detect d bits error? Okay, so I hope it is clear to all of you. Okay, so if you have any doubt, feel free to poke me or feel free to ask me to repeat. Now coming to the error correction. Okay, so how we can use Hamming distance for error correction. Now, in case of error detection, what I have to do, I have to just find out whether it is a valid code word or not. If we can find out that it is a valid code word, then I am good. Okay. But in case of error correction, what I have to do, I need to map every invalid code word to a valid code word. Right? So which I do not need in case of detection. Now to map every invalid code word to a valid code word, what I have to ensure that whatever code word, invalid code word are being generated, all those invalid code words are being mapped to a corresponding data word. Okay, so for example, if one invalid code word is generated here, this invalid code word should map to this data word. Similarly, if one invalid code word is generated here, that invalid code word should be mapped to this data word. Okay, so that is the kind of requirement that we have. Now, because of that reason, to detect these single bit errors, the minimum Hamming distance between two code words should be at least 2d+1, because the valid region or the kind of code word region which maps to a single data word, these two regions need to be non-overlapping. If these two regions gets overlapping, so for example, if I take another valid data word here and I have an overlapping, if that is the case, then if due to the error, one code word is generated here, I cannot uniquely say whether this data word can be mapped, this code word can be mapped to this data word or this data word. Okay, so that way I will have a confusion. So that's why the set of code words which are being generated for a particular data word, they need to be in a non-overlapping region so that we can individually and uniquely separate them out. Okay, so this is the kind of constraint that I have if I want to detect error, d-bit error using Hamming distance. Any doubt in this explanation? Or if you want me to repeat, also let me know. I will be happy to repeat. Okay. Now here is an example that how we can use Hamming distance for error correction. Consider these four code words. Okay, so all of them are 10-bit code words. Well, say the Hamming distance is, and among these code words, you can see that the Hamming distance is 5. Well, so in between any two code word that you select, well, you see that the Hamming distance is 5. Okay, so there are 5-bit positions where they are differ. Now, depending on my earlier example, we can either correct single bit error or we can correct double bit error. If there are 2-bit error, then the minimum distance between two code word would be 2 into 2 plus 1, that means 5, which is being satisfied error. So that's why we can correct either single bit error or a double bit error using this Hamming distance of 5. using this code word. Now, assume that if you receive a code word 1010100000, okay, you can see that, well, because I can have a single bit error or a double bit error, if I flip this bit and if I flip this bit, these two zeros, then I can get a valid code word. Okay, so remember that you cannot detect more than 2-bit errors. For matching to other code words, and you can get it here, this particular code word. Now, to match it with the other code words, to make it all zeros, you need 3-bit flips. Okay, to make it 00001111, you need 5, 6, 7-bit flips. Okay, so that way, for the other cases, you need multiple different bit flips, which is more than 2-bit. And that cannot happen because you can have at most single bit error or a double bit error. Okay. So that way, with this particular code word, even if you have 2-bit error or a single bit error, you can guess what is the original code word. But assume in another case, assume that you have received 1010000000, okay, and there are maximum 3-bit error. Well, so in that case, can you uniquely guess the code word? Okay, if there is maximum 3-bit error, so then you can change this bit, this bit, this bit to 1, and you can get this particular code word. Well, or you can change this 1 and this 1 to 0, and you can get this code word. Okay, so that means you can have multiple different options. You can do multiple different flips, and you can reach to multiple different valid code words. That way, the 3-bit error cannot be detected with 5-bit Hamming distance. Okay, so that way you can use the Hamming distance for error correction. Now the question comes that how you can encode a data bit and how you can put the or encode a data word to a code word using the Hamming code. Okay, so here is the method for doing that. So assume that the data you want to transfer is 1000001. Well, now what I want to do, that we'll use every 2 to the power x positions for the parity bit and the rest for the data bit. That means 2 to the power 0 means 1. So the first position will be used for parity bit. Then 2 to the power 1 means 2. That means the second position will be used for the parity bit. The third position, x equal to 2 means 2 to the power 4. That means the fourth position will be used for parity bit. X to the power 3 means 8. That means 8th position will be used for parity bit. The remaining position, that means the third position, fifth position, 6, 7, 9, 10, and 11 will be used for data bit. Now that way we arrange it. That means 1, 2, 4, 8. These are the position for the parity bit. And 3, 5, 6, 7, 9, 10, 11. These are the position for the data bits. Now you put the data bits. In M3 you put 1. In M5, M6, M7 you put 0. M9 is 0. M10 is 0. M11 is 1. Now, how do we compute the parity? Okay, so we compute the parity in this way. That means 11 position is the data bit. Okay, so 11 can be represented as 1 plus 2 plus 8. Okay, that means 1, 2, and 8. Well, along with M11, we can decide that what is going to be the parity. Okay, and here also we can work with the similar earlier idea of the parity bit. That way, either we can go for even parity or we can go for odd parity. Okay, here let us go with the even parity. Then for the 10, it is 2 plus 8. 10 is 2 and 8. Well, then 9 equal to 1 plus 8. The 9 we can keep it as 1 and 8. Well, and that way we can actually keep on deciding about the parity bits. Okay. Now give given a code with a Hamming distance of 3, 1 bit error can be detected. Well, so here we are putting generating the code word in such a way so that the Hamming distance is 3, and with a Hamming distance 3 we can correct 1 bit error. Okay, so let us see an example. Well, assume that a single bit error has happened in the data. Well, so if a single bit error happens in the data, so in that case, say for example, M5, an error has happened in M5. Well, now if an error happens in M5, then you can actually check the parity bit and you can find out an error in M5. Well, by looking into the corresponding parity bits. Now, if there is a parity bit, well, so in case of a parity bit, you check the that means that say for example in parity bit it was 0, the parity bit got flipped and it has become 1. Well, if that is the case, then you can find out a mismatch at M7, M6 and M5 where P4 has been used. So P4 has been used in 7, in 6 and in 5. So M7, M6, M5 there we can see a mismatch. Okay. Now the thing is that this P4, so because there are mismatch in the 3 data bits, and P4 is the common parity bit for this M7, M6 and M5. Okay, so that means the error is there in P4. Okay, so that way you can find out that there is a error in the parity bit. Now in the same way you can try with making 2-bit error, and you will see that you will not be able to detect 2-bit errors using this kind of idea of Hamming distance. Okay. So any error in this part? Okay. Then I would prefer to stop here today because the idea of framing and this concept of channel allocation that we can talk tomorrow and close the class for tomorrow. Okay, so let us then stop here today, and we can continue in tomorrow's class to complete the remaining part of the math layer. Okay, so if you have just try with this exercise about error detection and error correction, and if you have any doubt, you can ask me tomorrow, or you can drop me an email or may post on this Microsoft Teams. Okay, and as I have mentioned that we are going to have the class test on Saturday, so please prepare for that, and that will be at the same time from 4 to 5. Okay, any query?
Sir,
yeah.
In this error correction scheme, so how will we understand like what is the maximum number of bit that error can happen?
Actually, that is based on the experiments. Experiment in the sense that we typically for a particular wireless channel, what we typically do that we do a set of experiments and we transfer certain frames and find out that how many frames are being lost there, and from there we compute the bit error rate. Okay, so this bit error rate, say for example, if your bit error rate is 0.02, that means if you are sending 100 bits, then 2 bits, there is a maximum possibility of 2-bit error. So based on this kind of expectation or computation of the bit error rate for a particular channel, we typically design that what is going to be my maximum bit error rate that I should support in a forward error correction mechanism. But remember, that is a kind of estimation, right? So that way, there is no guarantee that the bit error rate is bounded by that number. So for example, typically in the Wi-Fi channel, we assume that there can be maximum 1 bit error with every frame. But that is the kind of assumption. If your wireless channel is much more, Wi-Fi channel is much more noisy, say for example, you have multiple different Wi-Fi devices which are trying to transmit data or which are creating interference. In the next class, tomorrow's class, we are going to talk about interference. If this kind of interference is there, then there will be loss in much more number of bit, or error in much more number of bit. So that is why typically in Wi-Fi you will see that we apply forward error correction and acknowledgement mechanism simultaneously. Well, so in Wi-Fi is being a highly noisy channel in wireless media. So that's why we apply forward error correction to recover from a single bit error, or sometime in the advanced Wi-Fi it provides mechanism to recover from 2-bit errors. But then we also have the acknowledgement mechanism. That means every frame that you are transmitting, the other end should send an acknowledgement. Okay, so we apply both simultaneously. The acknowledgement is typically used to ensure that we are not losing any frame, well, when there are more number of bit errors. Whereas the bit error rate, it is actually helping us to reduce the retransmission. That means for 1 bit error or 2 bit errors, I will be able to recover from the loss at the receiver side. So that way, there is a kind of trade-off, and we apply both simultaneously in practice. Okay, but that is a kind of totally based on experimental observations. There is no theoretical bound on it as such.
Okay.
Any other doubt or any other query? Okay, thank you all. Then let us continue from framing in tomorrow's class and close this part of the math layer to conclude our network course for this semester. Thank you. So see you tomorrow.
Thank you, sir.